As part of your lab report, you're going to need to make a ray tracing for part 1, a ray tracing for part 2, and a ray tracing for part 3. The lab does provide pages for you to do ray tracings. You don't have to use this paper. You can use any quad ruled paper like this to make your ray tracings. Just remember that all ray tracings have to be hand drawn and to scale, and make sure that you write the scale that you used on the drawing. And if you have any questions about drawing the ray tracing, please don't hesitate to ask me. So now I want to talk about the next part of part 1, which is we're going to be measuring the focal length of a lens using the near object method, and we're going to use lens A for this. Again, we're going to be working with our object image formula. And what we're going to be doing here is we're just going to measure for 6 different object distances. We're going to be measuring the image distance. So what we'll do is we'll place the lens here. The source will be fixed during this process, and then you'll move the screen until you get a clear image of the object. You will measure the object distance, and then you will measure the image distance and record that. Change the distance between the object and the lens, and again, find the object distance and the image distance. And basically, you want about 6 pairs of data. And then what you're going to do is you're going to plot the data, but we're not going to plot Q versus P. To make the analysis simpler, we're going to let X equals 1 over P and Y equals 1 over Q. Remember, P is the object distance, Q is the image distance. We're going to plot 1 over Q on the Y-axis and 1 over P on the X-axis. And when you do that, this equation becomes X plus Y equals 1 over F. If you solve for Y, then Y is minus X plus 1 over F. So the slope of this graph is always going to be -1, and the y-intercept is going to be 1 over the focal length. So you will do a curve fit to your data, a linear fit, and the software is going to give you the slope and the y-intercept. You just got to calculate 1 over the y-intercept. That'll give you the focal length. And don't forget to calculate the uncertainty. Then what you're going to be asked to do is to actually plot the lines that would be representative of the mirror, lens B, and lens C. That's it. Hello everybody. I want to talk about the next lab that we're going to be doing is the lenses, mirrors, and ray tracing lab. And for now I want to focus on the first part of part 1, which is the distant object method. The equation we're going to be using for the most part in this lab is this one. This is the object image formula for a thin lens. The P here is the distance between the object and the lens. The Q is the distance between the image of the lens. And F is the focal length of the lens. And what we're going to do in the first part is we're going to let the object distance be very large. Ideally be infinite, but we're going to let P go to infinity. And what we're going to do in this case, we're going to take an object, which is going to be this source that's plugged in right now, and we're going to put a lens in front of it, and we're going to produce an image right on the screen. So I have a lens here. There's 3 lenses we're going to do. One's labeled lens A, which is the lens with the shortest focal length. One is lens B. And then lens C is going to be the diverging lens. And you can tell which lens is the diverging lens because when you look through it, objects will look smaller when you look through a diverging lens. When you look at through a converging lens, objects will look bigger. So I have a converging lens here. And I'm placing it on this optics bench. And I'm going to focus the light from the source to a spot as best I can. And you may turn the lights off in the lab if you want to. So try to get the best spot you can, which which is what I have here. And then we can measure the distance between the lens and the screen. This will be the object distance. On these optics benches, they do have a centimeter scale. And also there's a mark on the lens holder and the object holder and the source holder, so we can accurately measure the distances. So this distance is basically going to be the focal length, because we're going to assume that P equals infinity. If you want to get more accurate results, you can take this lens outside, use the sun as the object, and find the image, measure the object image distance, the lens image distance on the sheet of paper, with a sheet of paper. You'll get a small spot of the sun on the paper, and that will give you a much more accurate value for the focal length of the lens. So you're free to go outside with this and use the sun as an object. Otherwise, you can use this setup where the object's at more than 3 meters away from the lens. So you're going to do this for lens A and lens B. Now for lens C, which is a diverging lens, we can't use this method because the diverging lens doesn't produce a real image. And so what you're going to do is you're going to take lens A and lens C and rubber band them together, and you're going to place them in the lens holder. Like so. Hopefully it holds. And then measure the distance from the lens to the image. Now there's an equation, there's another equation for this. 1 over f AC equals 1 over f sub A plus 1 over f sub C. Since you've measured this and you've measured this, you can solve for f sub C, and that'll give you the focal length of the diverging lens. All right, so for part 3, what we're going to do is we're going to use a candle for an object, and we're going to take a candle and place it within the focal length of the concave mirror, and we will also use lens A. So we're going to use this candle, place it inside the focal length of the mirror, and you're going to have to measure that distance as best you can with the ruler. Okay. You'll have the converging lens about 30 centimeters from the mirror, as described in the instructions. And then what you're going to do is find all the images that are produced. So you're going to move this screen in until you find all the images. I'll let you figure out how many images you're going to see and which optical element is producing which image. I want you to figure that out. Remember that this candle is inside the focal length of the concave mirror. And so what you need to do is, once you've made your measurements, you're going to need to draw ray tracing of this system that includes the object, any real and virtual images in it, and make sure, again, you draw it to scale. That's it. Okay, so we want to use the distant object method to also measure the focal length of a concave mirror. So here we have a concave mirror, and the source is all the way down on the bench. The mirror is different. It's going to be a little bit more difficult because the mirror reflects light. And so I have my mirror set up here, and I'm going to use this as my screen. And what we have to do is deflect the light from the mirror so that it actually hits our screen. And then I'm going to move my screen towards the mirror until I see the image of the object. So it's going to take a little bit of work. but it can be done. You just got to aim it towards the screen, and then once you can find the image, once you get a clear image of the object, then measure the distance between the mirror and the screen. And this is not going to be easy to measure because you're holding the screen in your hand, but we're just trying to get the best value you can get. Okay, if you want to, again, you can take this outside and use the sun as the object. That might be easier for you. So you do need two people to make this measurement because one person's holding the mirror and the other person's got to hold the meter stick or the ruler to measure that distance. Okay. All right, so I want to talk about part 2 in this lab. This is for a two lens system. And what you're going to do in this part is you're going to take lens A and place it about twice its focal length from the source. Set the source at 0 on the scale here, and then set the lens about 2 times the focal length of the lens. And then set lens B about 7 to 12 centimeters. So that's up to you from lens A. So here's lens A, here's lens B, and then you need to move the screen until you see an image. And what you want to do is measure the object distance, the image distance, and make sure you know the distance between the two lenses. And what you're going to do with it is you're going to create a ray tracing based on the data you collected. And this is a little bit more complicated because, well, you'll see. Okay, you'll see what happens in this. I'm going to leave that. I'll let you think about this system. But really, the goal here is to draw ray tracing. That's it.